We are continuing the conference with panel 3, which is moderated by Professor Mark Lemley, about quantum governance, national security, and geopolitics.
All right, great. Thanks, everyone, for sticking it out to the very last panel of the session. I'm Mark Lemley. I teach here in the law school, and I run the program in law science and technology. But we're going to talk about not law, or I guess science and technology, but not law. We're going to talk about geopolitics and national security. And I am delighted to announce that we are not going to sing. So we have that going for us. All right, let me briefly introduce our panel, and then I'm going to ask each of them to say a few short words on some topics, and then we'll open it up for panel discussion and then questions. So starting to my immediate right, Greg Berkin is a senior cybersecurity advisor at FTI Consulting. Vivek Chilukuri is the program director and a senior fellow at the Center for New American Security. Eran Kahana is a lawyer at Maslin LLP and also a Codex fellow here at Stanford and longtime participant and visitor at SLS programs. Professor Marie-Elisabeth Paté-Cornell is a professor at the Stanford Engineering Department and perhaps more impressive from my perspective, the founder of the MS&E department here on campus. And finally, Dr. Sujai Shivakumar is the director of the Renewing American Innovation Project at the Center for Strategic and International Studies. So we have a pretty distinguished panel here to talk about war, peace, governance, the international order, and so forth. Greg, why don't I start with you?
That's great. Thank you. Thanks, Mark. So I'm Greg Berkin, senior cybersecurity advisor and now quantum and AI for FTI Consulting out of Washington, D.C. FTI stands for Forensic Technologies, Inc. It's a 40-year public company, which most people haven't heard of. But the cyber practice is new. I'm originally a tech entrepreneur. Came from upstate New York, started one of the very first Apple Macintosh software companies for education 40 years ago. I just turned 60, so I'm feeling like an old man. But working in cyber on a daily basis is very instrumental and instructive because you learn some of the threats. And so one of the things I wanted to make sure we speak about is we're all about responsible quantum, but we need to be curiously irresponsible and think about the dark side. And we hear about that a lot in cyber, and so I guess we'll talk about that. But anyway, it's a pleasure to be here. I was here last year. It's an incredible conference. Thanks to Moritz so much. It's a wonderful, wonderful experience.
And Greg, do you want to say a little bit about talk a little bit about the Biden administration guidelines, or?
Yes. So my friend and boss at FTI, Anthony Ferrante, came from the FBI, head of cyber, and the White House under Obama. And the FBI in 2015, under James Comey, had a mandate that every FBI agent was to be trained on cyber skills. And so I got invited to the first ever CISO Academy at the FBI with 30 CISOs from Apple, Facebook, others. And I could see the understanding was urgent, the urgency for many of the cyber issues and election hacking. And FDI became kind of the firm after Anthony left the FBI and the White House to bring his cyber skills there. So he started the practice there. They had no cyber practice 8 years ago, and now it's pretty important working along with the White House to help define some of the standards and regulation and policy issues that are confronting all of us with cyber and the NIST standards. Now, the NIST stuff, if you don't know, came out of the Department of Commerce. It's actually a commerce-defined set of algorithms, and I guess we'll talk about that. But one of the NIST algorithms has already been known to be hacked, and so it's we really don't have in place the certain safeguards against vulnerabilities and things like that. So at FTI, we've been very, very active in trying to raise the awareness and the flag, and it's become a universal problem. So anyway, next.
All right, Vivek, tell us a little bit about what you do at CNAS and what you're thinking about in terms of quantum.
Sure. Thanks, Mark, and thanks to Stanford and Moritz for hosting us. I appreciate it. My name is Vivek. I lead the Technology and National Security Program at the Center for New American Security, which, if you haven't heard of it, which wouldn't surprise me, it's a bipartisan national security think tank in Washington, D.C. We cover sort of the waterfront of critical and emerging technology issues, but one of the areas that we cover is quantum, and this panel is well-timed because one of my colleagues who sat in this seat last year has just finished a report that's coming out next week on the state of U.S.-China competition in quantum computing. So I can sort of do my best to preview some of these findings and pretend to match her level of expertise, but she's terrific and unfortunately couldn't be here today. But that's principally what we're focused on at CNAS, is how to ensure U.S. technological competitiveness in some of these key areas like AI and biotech, but quantum is certainly one of them. And we can get into some of the weeds, but I think the headline is that, clearly both China and the United States have designated quantum as a strategic technology. They're both seeking quantum supremacy or quantum dominance, but they're pursuing very different approaches. I think in the shorthand is the U.S. has an industry-led, government-supported approach, and China has a government-led industry-supported approach. So it's sort of the inverse. And I think, in the final analysis, there's a lot of, doomsdaying about the state of U.S. quantum and where we are vis-a-vis China, and I think concern is warranted, but based on the analysis that my colleague did and our broader team did, there's actually there's a lot of reasons for optimism about the United States and our quantum future, and I think one of the reasons for that is we have an incredibly diversified quantum ecosystem. We have a quantum computing ecosystem in particular. We have viable companies and investments in all of the modalities, the key modalities of quantum computing. We have a massive amount of private investment, not big enough, arguably, but significantly more than any other country in the private quantum ecosystem, which is very important. And according to several key metrics, whether you're just looking at the physical, qubits, coherence, times, and error rates, we do lead in every modality, except for perhaps superconducting transmon qubits, which China has achieved sort of parity with us. And I think that diversified approach is really important because we obviously don't know which modality is going to prevail, and because we have horses in all of them, I think it puts us in a strong position. And I think a piece of the ecosystem that has received less attention is we are actually very strong. The QEDC, the Quantum Economic Development Consortium, did a study, and we actually are very strong in quantum applications. So I think a thing we can hopefully talk about later is it's not just quantum innovation, it's quantum implementation and quantum application, and that's a strength of the United States. But I think, I won't go on and on, but I think to rest on our laurels would be a huge mistake at the same time. The Chinese government, it's hard to get exact estimates of how much they're spending on quantum. It ranges from, McKinsey looked at it in 22 and said it was about $15 billion. The Congressional Research Service looked at it and said it was $240 million annually. So the figures varied dramatically, and that's not unusual for critical tech investments coming out of China. But I think it would be naive and it would be a significant mistake for the United States to be complacent about our quantum leadership, even though I do think we have an advantage today. There's plenty of steps we can take to shore up that leadership, and I'm happy to talk about that later. But I think two areas that probably need immediate attention are understanding our quantum supply chains much better than we do today and shoring those up, and two, obviously strengthening our quantum-specific and general STEM workforce. I think those are the two arguably most immediate things that we need to focus on. But I think there's also plenty of reasons for optimism, and we shouldn't be too gloomy about America's quantum future.
Great. And if you were here for lunch, you saw Amin Ali give a pretty remarkable talk on the sort of state of access to raw materials in various countries throughout the world. I think it is a complex and multifaceted problem. Eran Kahana, you're going to talk to us a little bit about the sort of ways in which AI overlaps with quantum.
Right. So almost 16 years ago, but who's counting? I started at Stanford at Codex as a research fellow looking at the intersection of law and AI. And it was in 2016 that it suddenly dawned on me that there are some similarities with quantum. But nobody was talking about quantum, at least nobody that I knew of. So I'm very grateful to have met Moritz, because now there's somebody I can talk to about quantum, and other people that I have met here. So I was, one of my projects that I've been working on now for a little over a year, I call it loosely the AI Lifecycle Core Principles, and you can look it up on Google. It's the first non-sponsored search. I obviously didn't pay for it to be sponsored, so it's right up there. And I have counted 37 core principles. And what are core principles? They are accountability, reliability, robustness, resilience, trustworthy, and so forth. Those are core principles. And I started thinking about what do they mean, because I was reading about them and I could not figure it out. What does this mean? What does accountability mean? When I read things like from the OECD and the IEEE and other sources, it was hard for me to keep track of what they meant by these. So I started developing a list. And that list is now a very large chart with a lot of notes, a lot of discussion about what these different principles mean. And then I started thinking, okay, well, how does this apply to quantum? And as I started thinking about quantum, and then I read Moritz's 10 principles, it suddenly dawned on me that there's a lot of similarity. There's a lot of things that you can map, to use the NIST approach, between the core principles in AI and the RQI, the responsible quantum computing principles there. And that's really where it became obvious to me that the most important part of quantum, let's say the principles, I took it from the AI side. And what it is governance. And how did I come up with the idea or the concept that governance is the most important principle? I looked at the NIST AI risk management framework, and I dissected it. And I mean, I dissected it. I used a mind managing program called Mind Manager, and I dissected the RMF, and I looked at every task, and then I mapped it to the core principles. And it was surprising, well, maybe not surprising, but I saw at the end of it that 48 tasks out of 90 in the risk management framework are all related to governance. And it was not surprising as I was thinking about it more and more. None of it can happen. None of the things that the NIST talks about can happen if you don't have proper governance. And governance is not regulation. I'm not talking about regulation. Governance, I mean what companies do internally, their processes, their procedures, their practices, their culture, everything that is basically rained down from the board of directors to the C-suite down to every single employee. That's the governance I'm talking about. Nothing can happen, even the 10 principles that Moritz has, none of these, actually 8 of them, 80% of them, relate directly to governance. So you cannot have anything actually operationalized, anything executed without proper governance. So that's where I started pouring a lot more emphasis to understand it. As a practicing attorney, I used to be a closeted academic, not so much anymore, now that I also teach at the University of Minnesota Law School as an adjunct professor. But I also like to think about the practical elements of what I do, not just have it as an academic endeavor, but look at the practical aspects. So the practical aspect is, how can we make money as lawyers? For those of you who are lawyers here, that might be of interest. How do we make money on this? So to me, it was like, through this work, I can integrate myself better with clients and help them understand what they need to look at with their policies, procedures, and practices with respect to governance in AI. And then ultimately, when things mature enough with the quantum field, that will be imported into that.
Okay, great. And I think we're also going to hear a little bit about AI from our next speaker, Marie-Elisabeth. And you have slides.
Yeah, you know what? I have my slides in front of me, so don't worry about it.
No, there they are.
Oh, okay, great. So it tells you what I'm going to do.
Do we have a clicker for you?
Yes, right there.
Good.
Clicker. So I have to click?
Okay. Green one.
The green one. Perfect. Okay, I'm going to talk about artificial intelligence and support of risk assessment and risk management, which is my job. That's what I teach at Stanford, applied to engineering systems in general. The problem that I have is the preferences that are encoded in these systems, and even more with quantum computing. Does it work? Yes. Yeah. So there are two roles of artificial intelligence in risk analysis. The information phase includes uncertainty with very large databases sometimes, and it has to be updated, and it has to be neutral. Now, in the decision phase of risk management, it's based on that information, but also it has uncertainties, and it requires preferences and a risk attitude. And we're going to see that risk attitude is really the problem. Okay, so we have the problem is a potential mismatch of preferences between what's in the AI system, fixed algorithms and risk attitude, but again, they may not reflect the preferences of the decision maker who uses the recommendation of AI. So the decision system must be flexible enough to ensure that this potential mismatch is corrected and that the preferences are those of the decision maker. And I have developed examples that I won't have the time to talk about, but in medicine, national security, automated vehicles, and sports, sailing race. That was the first time I encountered that an AI in that field. So let me give you an example of a medical doctor and a patient. And the situation, and it's a real case, a patient without symptoms is in the doctor's office after a mammography. And the information that they have is a negative result of a needle biopsy. And the decision is, shall we have additional tests? The doctor has access to an AI system that recommends surgical biopsy based on the patient's age and on the average decision in a crowd. But the patient doesn't want to. So the problem is the surgical biopsy after a negative needle biopsy. Should we do it? There are 4 different risk attitudes: the analyst, the surgeons, the doctors, and the patients. So if the AI recommendation does not fit our preferences, the patient's risk attitude should prevail, and the question is, how can it be done? Access to more information, better understanding of algorithm, and in this case, the rejection of the further biopsy. Okay, now let's talk about the effects of quantum computing in a general case. We have an acceleration of the information gathering, processing, and updating, quicker detection of relevant data, and access to of the system to larger potential sources of information.
I think go back one slide. You're one slide too far ahead.
Ah, no,
Back.
no, the reverse. Okay, thank you. So the quicker updating of uncertain variables in different data categories and the potential increase of the number of data categories, restructuring of the data set. But even greater difficulty if there is no time to identify and assess the information sources and the risk attitude involved in the decision recommendation, where I met that problem the most serious way was in national security and the use of drones. Okay. No. So the decision problem now: make responsible decisions under uncertainties, possible options in future implementation. Let the computer make and implement automatically the decisions generated by the quantum algorithm. Is some risk, but it may be quicker than the adversary. For a human decision maker, avoid the use of quantum information if it is received too fast to intervene. And again, I was mentioning the use of drones in defense. Set up criteria permitting to decide whether to adopt or decline a system's decisions based on uncertainties and outcome magnitudes. That's an intermediate solution to this problem. So, my conclusion: we need to make the AI or AGI system transparent and flexible in decision-making or advice. For information processing by a computer system, whether it's classic or quantum, Disclose the information sources and risk attitudes, if possible. For automatic decisions, including risk management, disclose the rules of actions, the encoded preferences and the risk attitude. Disclose the system's dynamics, including the updating of information and the encoding of preferences. Now, preserve the ability of the user, particularly in medicine and in defense, to understand the effects of the system's risk attitude and its influence on recommended or automated decisions, to accept or not a system and its recommendations, and to ignore the AI system and follow his or her knowledge, of course, at one's risk. The first time I heard about this was my husband, who is a high-ranked admiral, who was at the head of the strategic command, and who told me one day that you don't take what the AI system is telling you without being extremely careful. So you use your own judgment if it doesn't quite fit the one that you see. And that's it.
Okay, thank you. And finally, Sujai is going to talk to us a little bit about American competitiveness.
Thank you. I find myself as the last speaker, so everything has been said, but not everybody has said it, as the saying goes. I also realize that I'm what's standing behind you and a nice reception outside, so I'll try to make the points quickly. I think let me take the advantage of actually being the last speaker to sort of paint a larger portrait and see how some of the themes that have been raised today kind of fit together. I'm a senior fellow at the Center for Strategic International Studies. I think we have a little bit of a rivalry with Vivek as to who the preeminent national security think tank in Washington is. I like to think
it's a bipolar world.
Yeah. But as one of the leaders in national security analysis, we like to think that we set the definition of what national security is, and increasingly we come to realize that the innovation system itself and all the different components that are all interconnected is itself an innovation, itself a national security asset. And what we have what we've seen over the past few decades is sort of an experiment in terms of how do we offshore manufacturing, and then the follow-on effects of offshoring manufacturing. Not only did, for a period, the U.S. industry get the China price, a temporary phenomenon, but we also didn't invest in our workforce as a result. We didn't invest in our infrastructure as a result. We didn't bring our regulations, including environmental regulations, into the modern period as a result. And now we are sort of forced to play catch-up. We have the CHIPS and Science Act, as was raised this morning. And some of the reshoring of the semiconductor industry, the chips industry, is actually forcing a lot of these functions in terms of, making sure that we are constructing again, that we are building our infrastructure again, and that's putting a lot of pressure on different parts of our innovation system. Now, semiconductors and quantum is sort of a study in contrasts. Semiconductor industry grew globally in a period of relative geopolitical calm. And so a lot of the firms and the firms sort of grew and located where they thought it was advantageous for them to locate, multiple accidents of history, so forth. So what we have today is highly geographic concentration of the industry in East Asia. You also have the rise of China as not only a near peer, but also a geopolitical competitor today. And then you also have a couple of other factors. One of which is the fact that the demand for semiconductors is doubling within the next by the end of the decade. Multiple other factors creating a sort of a perfect storm for the industry. For quantum, you have actually an opportunity to grow the industry, which is now at the inflection point from being primarily an R&D effort to actually being an industry. So how do you create the framework conditions under which this industry can grow globally, keeping in mind the geopolitical constraints that we face today. How do you make sure that it is distributed? How do you make sure that there's enough of the industry in the United States, and while also connecting it to global partners in Europe and elsewhere? So these are sort of the broad challenges. And what has been our response, at least in Washington to date, has not been that promising. I mentioned chips and science. If you look at the science part of chips, yes, we did authorize the doubling of the NSF budget, but we do the two-step in Washington. We authorize something, and then the amount that is actually appropriated comes later. And if you actually look at the appropriations, we've actually cut NSF's budget by 8%. And this comes at the same month when the Chinese have increased their R&D budget by 10%. So we are not actually playing a serious game here. We also need to grow the ecosystem for a quantum industry in the United States. And here we need to understand what industry's motivations are, how can we encourage industry to grow and connect. There are scale-up needs. The industry has grown up to a certain degree, but for the next, the needs were in the millions. Soon they will be in the 20 to 100 million range, and then in the billion range. So how are we going to make sure that the capital needed for this expansion is in place? We have relatively modest drivers in terms of procurement, but how do we get NASA, DHS, other agencies, the Department of Defense, to procure more to try to grow the industry? How do we positively network with countries like the United Kingdom, the Netherlands, Denmark, as we saw today? There are serious challenges that firms tell us in cooperating with even European allies. So how do we get past some of those challenges? And then how do we simplify the regulatory environment? And that issue has been raised by multiple speakers today as well. So the broader challenge is how do we grow this network of connections, suppliers, different types of technologies within the United States as a national security imperative. So I'll stop there. Thank you.
Great. So let me use that as the jumping off point for some questions to the panel. So you just mentioned the national security imperative, right? I guess I'd love to hear a little bit about, more about sort of how U.S. domestic policy is going to interact with China. I mean, this is a technology that seems like a sort of global technology and a global problem. We heard a little bit from Vivek on sort of where we think China is and isn't on the technology. Is this something where we think we're going to see continued international collaboration? Is this something where we're going to see a move in the United States towards autarky, towards trying to pull things back within the United States, restrict export of quantum technology and so forth?
Well, if you think of the innovation system, as I mentioned, which is sort of a network, neural network, you can use various metaphors, connections of gears, you have manufacturing, you have research and development, you have education, you have capital networks, but you also have the political and policy network, which is an important part of this. Right now, that gear is stuck. We've been told, I've been told by people on the Hill, just wait 6 months. Well, I don't believe anybody's given the Chinese, a 6 months pause in the policy process to get their act right. We have the NQIA reauthorization sitting there. I think it's passed the House, but there are no plans to take it up in the Senate. I think we discussed that this morning as well. So the system is dysfunctional and it is paused. So we actually need to get people at the grassroots, such as yourself, to talk to your representatives, your congressmen. These things actually help when you actually go out and engage with them. They respond, and the staff the staff responds as well. I think it's important to paint this again as a very bipartisan effort, which it is. There's again, the chips and science. We need to think about the future. There's again this sense in Washington that we've done chips and science. Okay, we can go on to the next thing. When we did the Cold War, we didn't fund DOE labs for 5 years and then stop. We built these for decades because that is the length of the engagement that we saw as necessary. So again, we need to be thinking much more long-term, much more strategically about how we grow this industry, in which direction it grows, what sort of problems it is going to have to solve, and so forth.
Mark.
Yeah, please.
For my sins, before I joined this think tank, I worked in the United States Senate for 6.5 years, and on a lot of the issues related to the chips and science and the infrastructure law. And I think, one thing that just becomes apparent to anyone who's either worked on the Hill or observed the Hill, to those with the misfortune of doing that even, when China is on its 13th 5-year plan, and we are funding our government 2 weeks, 2 months, 6 months on a good day at a time, it's pretty clear how that's going to play out over a few years and a few generations. There's a level of seriousness and farsightedness in Beijing that in some ways is admirable, and we should absolutely strive to do better in terms of our, not just quantum tech policy, but you could name it, biotechnology, AI. We woke up one morning and realized that 92% of the advanced chips that we needed were in Taiwan. We woke up one morning and realized that Huawei had wired a lot of our rural telecom infrastructure, and we may wake up one morning and realize that we've been beaten in some other key technology areas because we don't have the infrastructure. We don't have even at a bureaucratic level, we don't have the horizon scanning capabilities to integrate what our intelligence community is seeing in terms of technology trends abroad with what the federal agencies like Commerce are seeing in terms of domestic trends, and integrating that in a fused way to surface problems before they arise and tell policymakers at OSTP or the National Security Council that to ring the alarm and say that this critical supply chain for an emerging technology, we think superconducting is the most viable. I'm just making it up. The most viable modality, but we are critically dependent for this input. That's a problem. We don't want to wake up in a world where we're dependent on Russia for certain inputs, and all of a sudden they have massive leverage over our ability to make quantum progress. So I completely agree, and I think not beyond just the domestic work that needs to happen. One of the realities of the quantum supply chain is because we don't know which modality is going to prevail. Unless we are prepared as a country to indigenously produce every single input and material and sub-application for every modality, we need partners. We need allies. And the good news is that, unlike China, to be honest, the United States has an unrivaled network of allies and partners around the world, a lot of them technology-leading countries. And I think what a far-sighted quantum policy from Washington would look like would say, here are the 3 to 5 key modalities we think are most promising. Here is the supply chains vulnerabilities that we have. Here's what we need. Who makes them? How do we make sure that we have access to what we need from countries that we can rely on that won't leverage it against us, and then act accordingly. And I think on the workforce piece, it also relates to the allies and partners question because, you just look around this campus, you look around any campus that's leading technology policy in America, we rely a ton on immigration and the best and brightest around the world. And this is another area where Washington has taken one of the biggest advantages of the United States in the technology competition and turned it arguably into a headwind, where instead of processing green cards, we have an absurd green card backlog in this country. So we should be innovating and thinking of critical and emerging technology visas across the Five Eyes Alliance or across NATO countries. There are lots of opportunities for policy innovation here on the immigration side. But I'll go on because there's a lot to talk about.
So all that's on the input side, right? Sort of we need supply chain, we need to get raw materials, we need to get labor, we need all these things. But I also want to talk about the output side, right? So we spent the 1990s fighting over whether computer encryption was a munition that we should prevent from exporting to countries who might take that technology and use it. Are we going to do the same thing here? Should we? Is this? I guess what I'd love to hear from various people are the trade-offs on right. Should we limit what can be exported on quantum technology?
Sorry to the think tank types from Washington are
we love to talk, yeah.
But there's sort of two aspects to it, as has been described. One is sort of the promote and the protect side. And right now what we're seeing is a lot of action on the protect side, which is export controls. Export controls work well when you have a fairly discrete technology that is slow moving in terms of innovation. It doesn't, and it also worked well in the Cold War when you had a competitor that was not as innovation sophisticated. Today we have a near peer who is basically ahead on some technologies, very close to us on others, and so trying to create barriers to their advancement slows them down a bit in the short run. But it really encourages them to actually innovate faster and in different areas. So if you are trying to create, block the ASML tools from reaching China, they will then innovate on other materials, other types of packaging, other areas of the technology, and which is anyway where the future of the innovation trajectory goes. So we actually do need to be thinking our national strategy should be one of growth, and as Vivek said, harnessing our natural advantages. And we don't seem to be, we still, the export controls is a new shiny object in Washington. And we are kind of enamored by that, and we are not really focusing on what we need to be doing, which is sort of the focus of this conference here.
All right, so let me ask a question that I think relates to that, but sort of brings in the private sector and not just the governmental side, right? We're seeing a lot of debates on the AI context about whether, from a regulatory perspective, as well as an innovation perspective, we ought to be encouraging open or closed systems, right? So an argument for closed systems run by large companies is there's a central choke point and it's much easier to regulate, right? The argument for open systems is if you let a whole bunch of people play with these tools, right, you're going to get a wider diversity and variety of innovation. But I think that relates to the sort of export to the international issue. So let me ask, and maybe ask some of the sort of private sector and academic folks to sort of take the lead on this. Should we be aiming for open systems in quantum or closed systems? Do we want to try to lock this down among a few companies, or do we want to try to sort of get as many people access to quantum technology as we can?
The NIST standards are kind of open because you're getting input from industry on different algorithms, but the challenge with an unbreakable encryption scheme is that it's got to be proven, and it's got to be math-based, and it's got to be a solution that everyone agrees upon. And so it's going to be difficult to legislate ahead of the challenge or this transition to AI and quantum. It's not an easy thing. We were talking about history before. This is a kind of a crude example, but in the 90s, remember the DVD, the digital video disc? When it was introduced, the Hollywood studios, to put their content on a DVD, had to encrypt the data. You had to encrypt the DVD. But at Intel, to allow a DVD to play back on a computer, they said that the Pentium processor couldn't decrypt. If you encrypted all the data, you'd never be able to watch the DVD because it would take too long to decrypt it. So they legislated 10% of the data would be encrypted on the disk, and they came up with a scheme called the Content Scrambling System, CSS. Within 6 months, a 14-year-old Norwegian hacker cracked the scheme, and it was about the key distribution for the keys to lock up every title. And so, crude example, but it's about gaining consensus and a governance of the encryption, and we're sort of on that on a massive scale, how to do that for all of our data, all of our networks, all of our transmission, and that's a real challenge.
Well, I just think on the open or closed, my views on it are very much influenced by a hacker named George Hotz, and if you don't know who he is, look him up. He's a fascinating individual. There's a fantastic podcast with Lex Friedman. It's the 3rd episode. And I think, to me, it's really a question of, how do you align the technology for the benefit of mankind? If it's open, there's the argument that it's better. If it then closed is just for a few. Open is for the many. But I also think about the phenomena I call the power of augmentation when it comes to AI, which basically means anytime you introduce AI into something, you create bigger problems, bigger challenges. And I think we'll have that in spades when it comes to quantum. So anything we introduce quantum into will become even more problematic, more difficult, more challenging. I'll say this about legislation. We will never have legislation that comes before quantum. It'll never be first. Legislation will be an evolutionary process. It'll happen over time. There'll be a lot of failures, challenges, and things that we haven't even thought of. We may proceed into an open environment, then figure out, oh shit, this is not any good. Sorry for cursing. And then we move into a closed environment, and then back to an open environment. And so we will not figure this out definitively, even though there's this urgency that I hear frequently. We got to get this right. We got to get this in place. It's just not going to happen. And a lot of this is informed also by Yann LeCun, who is the chief AI for Meta, chief scientist for Meta. And he also takes the approach that this urgency is misplaced, it's fabricated, and we need to slow down and reduce our expectations, reduce the flames.
And is that a claim about, is the never claim a claim about the US, or is it a worldwide assertion?
I can only speak about what I think about the US.
Yeah, okay, right. Because I mean, it's our experience historically with sort of predecessor technologies has been the US is much less likely to sort of regulate in advance and to respond to problems as they arise. And Europe is, I think, much more likely to try to build a framework to direct the technology. We've already seen the sort of enactment of the sort of AI Act in Europe, for instance.
And Mark, I would just quickly observe that the Senate had 12 inside forums on AI over the past year, 12, and a lot of members participated, and Leader Schumer and 3 other members, they released a bipartisan, essentially, white paper, which was pretty light on the regulatory side, and essentially said, which fair enough if you think the technology is evolving, but part of it was we don't understand it well enough. It's still too developing for us to be passing regulations at this point. We should just take it more piecemeal, and that's on AI, something that's I still think poorly understood, but much better understood relative compared to quantum. If you think that the Hill doesn't understand AI, wait till they learned about, photonic and superconducting.
But the good news is it's super intuitive. So.
Exactly. Yeah. So I agree. I don't think legislation is happening anytime soon.
And that's okay.
Yeah. It might be a good thing, right? I think the internet example has some interesting tales in both directions, right? But one of the things that the sort of early internet legislation, some of it was explicitly deregulatory. We're going to leave things alone, but some of it also just sort of made assumptions about what the world was going to look like that turned out to be wrong. We have an entire model body of laws adopted in some states for public key intermediaries that we wrote in the 1990s because everyone knew that nobody would possibly sort of give money across the internet unless there was a verifiable, trusted third party that was not the party you were doing business with that would hold your credit card information because you wouldn't just share it with a stranger. And then it turned out we were all perfectly happy to share our financial information with strangers, right? And nobody's ever used that system. So you can certainly imagine regulating on an assumption about how the technology is going to develop and then just watching the technology kind of move off in a different direction. All right, so let's open this up to questions. We will have a microphone that comes around to you.
Hi, thanks so much. This was a really fascinating overview. In an earlier panel, Professor Cohen raised the question as to what was fundamentally new about quantum technology, if anything, particularly also from a regulatory perspective. And obviously in law, we like to think in analogies. Is there an example of technology regulation that could serve as a positive example for quantum regulation as well?
Well, I think that AI serves the model that I think about. After our prep meeting that we had a couple of weeks ago, I wrote down how we do AI will tell how we do quantum. If we are successful in how we introduce and bring AI into society using all 37 core principles, and the similar ones that relate to quantum, the 10 principles in quantum, I think we'll have a good experience. So I think paying attention to what's happening in AI will be ultimately instructive for quantum as well.
I think just to add to that, we need to be taking a much more proactive approach to standards. Obviously NIST is an agency, but they are very much rely on industry participation to establish those standards. Again, since this is a sort of a geopolitical panel, the Chinese have their 2035 standards strategy, where they recognizing that the country that sets the standards is the one that calls the tune. So the U.S. has long been the leader in standards, but it's a bit, they've taken that for granted. And so in terms of being proactive in a number of standard-setting agencies globally and so forth, there's a need to revive our attention, our involvement in a lot of those activities where a lot of these, these basic, the vocabulary, the grammar of technological cooperation is set.
I'll just jump in with two more quick examples. One is happening in real time, which is the CHIPS Act. I mean, it's not regulation, but it is a test case for whether the United States can do industrial policy on a very complicated technology. And if we succeed, it could create the political momentum to do it in other areas as appropriate. But if it fails, it'll turn into, I don't know if people remember Solyndra, right? This loan that the United States made to, an energy company in the Obama administration. It became a poster child for why Washington should not have anything to do with technology and clean energy and investment, which, they forget that same program invested in Tesla. But besides the point. So that, if it works, could be really important as a demonstration. And if it fails, will also be really important in the other direction. And two, so it was I thought, Mark, you were talking about Section 230 in a section, and I'm certainly not as calling for a new Section 230 or anything, and I don't even know how it would be relevant to quantum, but I think the point is that the idea around Section 230 was to create an ecosystem, to enable an innovation ecosystem so that internet startups at the infancy of that transition could put stuff on, host content without getting sued into oblivion. The problem is that Washington never revisited it, even today, 25 years later. This is maybe too optimistic, but if we could have a Washington that could regulate with the nimbleness and dexterity that understood the different phases of different technologies, and that what technology that may be appropriate in an early stage is no longer appropriate later, and actually go back and adjust it in a timely way, that may be too much to hope for, but yeah.
That's a reasonable thing, yes. And so I think on that point, right, and with great respect to my colleagues, including the one who's running this this conference, right, when I hear ideas like let's have an FDA for quantum technology, I get nervous precisely because I associate that with it's going to take a long time, it's going to cost a lot of money, and it's not going to be the startups that are the ones doing it, right? We're going to sort of come in and sort of pre-decide where the innovation happens. The paper I think is more nuanced than that. I recognize, but I'd much rather see us sort of have regulatory rules that encourage startups and new entrants and ideas that don't come from existing major players, at least at the early stage, and then understanding that as problems arise, right, we do need to be able to come back and revisit it, as Vivek suggests. Yeah. Question over here, Alexander.
Okay, so on one hand side, I think that this point on that we won't have legislation until things go bad is like a little bit of like a sad approach. That, for example, we see that some legislation was only put into practice after people were poisoned, or we had the thalidomide catastrophe. So I think this is like a bad way to make legislation. So do you think that quantum does not pose so big risks that you can just wait for the risks and then put the legislation in place? That is one question. And the other question that I have is, do you think that there might be a difference from quantum to AI in the case that quantum technology covers very broad ranges of different physical topics and technologies, while AI is a little bit more focused on a specific type of technology, versus sensors towards quantum computers cover very broad ranges?
So I'll take at least a little bit on the second piece, right? So I think it's absolutely right that, right, one of the issues is we mean so many different things when we say quantum, right? Because we're really talking about a sort of scale that has different input into a variety of different decisions. That I don't think it makes sense to say let's have a quantum regulatory body, right, or a quantum rule that applies for everything, right? Because we wouldn't, to take one example, I mean, all modern semiconductor manufacturing operates at the quantum scale, but when people talk about the sort of coming problems, I don't think they're talking about semiconductors will get faster, right, and we need to regulate that and control it, right? I think they're thinking about a different piece. Maybe it's sensors, maybe it's quantum cryptography, breaking cryptography, right? But so thinking then about regulating specific applications seems to me to make much more sense than let's regulate quantum as a whole.
I don't think that it's realistic to think that we are going to have regulations in advance of quantum being deployed and that we will, by that, save lives. I think if Jan LeCun recently wrote on LinkedIn, he analogized it to the development of the aircraft and the use of aircraft to transport people and cargo. That took decades in order to get to the level of safety that we are in now. There is a tendency of things just to take time. And to think that things can instantly shake and bake and you got this thing all set up is just not realistic.
So I think one issue that is in fact worth having the conversation over, right, is the failure point a small problem or a gigantic problem, right? And I think the worry is, right, this feels like nuclear weapons, right? And we see the same conversation in AI, right? If we think the worry is we're going to blow up the world, right, then you want to regulate much more aggressively in advance against the risk of that. If the worry is some bad things will happen and people will get injured, right, there will be misinformation on the internet, and then we come and respond to that.
So but there's an alternative to regulation, a much more nimble alternative, and that's standards and best practices and guidelines. So you have NIST, for example. NIST is US based here, but it's influential across the globe. You have ISO, influential across the globe. That's not based in the US. There are ways to get companies to do things that are not regulations. Regulation ultimately is the slowest, in my view. We spend a whole day in class just looking at that in my law school class. Regulation, ultimately the conclusion is the slowest mechanism to get things done. You can be a lot more efficient with following standards and guidelines and best practices.
Okay, I'm getting the red card over here, so I think we are going to continue this conversation at the reception outdoors. So I will turn it back over to Maurice, and thank you panel.
Thank you so much for a great panel. Folks, this brings us to the end of the second edition of the Stanford Responsible Quantum Technology Conference. Such great energy. I think we all learned a lot about quantum simulation, materials devices, governance and national security, societal impact, quantum AI hybrids, and novel use cases to be explored in diverse multidisciplinary settings. I'm really having a sense of community and in the spirit of making a positive impact together, which is really great. And I'm also excited about designing pro-innovation regulatory frameworks for governments worldwide, taking standardization as a starting point, about the practical systemic thinking this requires, and about our own Stanford quantum incubator that will help build a competent, values-based quantum ecosystem here in the Valley and beyond. And we are actively steering things into a direction we hope to be beneficial for all groups in society on the planetary level. And I'd like to consider our combined efforts as a research agenda outlining future research priorities in a golden triangle of academia, industry, and policy. So I hope you made a lot of new friends today and that you can stay with us during the reception. We have snacks and drinks, and the band Loeb will make sure it's groovy. Thanks to our sponsors, Novo Nordisk Foundation, Intersable Copenhagen, Daiki for supporting our mission. Thanks to the speakers, the moderators, the musicians, our timekeeper Alexandra, to Jody and Giselle and Monique for helping me organize and promote the event and getting the piano here in time, to Monica from Residential Dining for the wonderful catering, for helping us with the podium, letting us do the sound checks yesterday on Sunday. Thanks to Scotty's audio-video team, to Scott for taking pictures of the event, and thanks to Adriana from Music Department for generously letting us rehearse the musical interludes in Brown Music Center over the past months. Thanks to the students for your exceptional performances, to Constanze for writing a summary for our blog, to Jenhee and Katie for being so supportive of our center in so many ways. And thank you all for being such a cool and clever audience. Special thanks to Professor Mark Lemley, who has been such an inspiring and caring mentor to me over the past 5 years. And thank you for your support and for letting us be creative. As we stand on the cusp of the second quantum revolution, we face unprecedented opportunities and challenges in the field of quantum technology. And we hope to see all of you back next year at the Stanford RQT Conference 3.0. Thank you.
But he's heading west from the Cumberland Gap to Johnson City, a like the wind and the rain. Rock me, mama, like a southbound train. Hey, mama, rock me.
All right, thank you.
Thank you very much.